First of all, I welcome everybody for our joint webinar, Influence of Sample Preparation of Solids to Quantitative XRF Analysis. And I just would like to ask Carmen just to introduce herself, please.
Hi, I'm Carmen Kaiser Bruckmann. I work for the company called Rigaku. We make X-ray equipment, yes, my background is I'm analytical chemist and worked for many years in industry, but now I have the pleasure of working with potential customers and, of course, our solution partner like Rainer. Yeah, so thank you.
Okay, thank you, Carmen. My name is Rainer Schramm. I'm the CEO from FLUXANA, and I work since more than 35 years in XRF and just doing XRF development, application development, helping customers to set up their XRF solution. And our focus in FLUXANA is more on the sample preparation technique and the application development. Yeah, and I would like to start here then. So I do the first half and Carmen does the second half of this presentation. So I will concentrate on the sample preparation and then Carmen will show you the measurements of the samples we prepared. And so in this way, we split the presentation between each other. We thought it might be quite interesting to see what kind of sample preparation you can use to prepare solid samples. And I think it was Carmen, she had still a few samples in her lab, and like sodium sulfate, sand, calcium carbonate, and talcum. And so we would like to use these four materials to present the different sample preparation techniques and then, of course, also the influence to the results. But of course, I will start with the XRF principle. I will talk about pretreatment grinding, then particle size effects. First preparation technique, powders and sample cups. Second technique is powders as press pellets. And the third one, powders as fusion. So then we have these samples in all three preparation possibilities, and then Carmen can easily present finally what is the influence to the result. And of course, we will make a conclusion in the end. Yeah, when we talk about X-ray fluorescence, for those of you who are new in the field, what happens in our instrument is that the X-rays from the X-ray tube, they hit our sample. And then in the sample, of course, you have an agglomeration of different atoms, which make finally 100% of your sample. And these atoms, they are ionized by the X-rays. That means that one of these inner electrons of each single atom will be taken away, and an electron from a higher shell will fill up the gap. And then this difference in energy, like you see it here, this could be sent out as X-ray fluorescence. There are also other effects which can happen, but one of these is X-ray fluorescence. And with increasing atomic number, this effect gets more and more intense. And what we see in our instrument is then a kind of a line pattern, like here for iron, so that we have for one of these filling gaps, the Ka-alpha line, and for another combination, the Ka-beta line. And this way how it presents, this is always constant in XRF. That means when you have iron in your sample, you will always see this kind of line pattern. So it's always good to have a look into the spectrum to identify the elements. But which elements can we analyze? So the blue ones are the most common ones. So starting with fluorine down to uranium. So let's say out of the radioactive elements and perhaps the gas elements, you can analyze every element. The very light ones down to beryllium could be also analyzed, but then you need really a special adaptation of your instrument. And that's why it's not so common. It's just a question if you really need this information. Yeah, and now let's talk about sample preparation. What techniques are available nowadays? So the very easiest thing is that you use a kind of a sample cup and you just pour your powder inside and then you measure it. Or you have liquids, that's even more easier, that you just pour a liquid into a sample cup and measure it directly. Another possibility is that your sample comes as a piece and you can directly analyze it as long as it fits in your measuring chamber and in your sample holder. This would be also possible for polymers. You could melt into a form so that you can adapt it to the X-ray measuring system. Another possibility is that you make press pellets out of your powder, and last but not least, that you digest your sample into a glass and you make a so-called fuse bead. So this is our way how we can present samples to the XRF. And today I would like to talk about this one, solid material in a sample cup, solid as a press pellet, or solid as a fusion. But of course, there are some physical effects we have to investigate so that we understand a little bit better why is there a difference between the different sample preparation techniques and why we have to think about which technique might fit to our requirements. And for that, we have to know that, of course, our X-ray tube is irradiating our sample and our detector is watching the sample. That means, first of all, the X-rays from the excitation is going into our sample. That means there's a certain energy. This will go into the sample depending on the matrix in a certain depth. And also there then will be the X-ray fluorescence created, and this fluorescence radiation has then to leave the sample. That means, again, it has to go through all the way until it leaves the sample. And we have absorption on the way in and absorption on the way out. And this depends, of course, on your sample material. And this I will explain more deeper on one of the next slides. First of all, we have to think about that when we have just a powder, and it could be a pressed pellet or it could be just a loose powder in your sample cup, you have particles. And of course, the particles are in a lot of materials not always the same. So it could be that you have one particle which is more rich in silicon oxide, and you have another particle which is more rich in calcium oxide. And then, of course, it makes a big difference how deep you analyze your sample. And so it is important, is your sample really homogeneous, or is one sort of the particles just lying here on the film, for example, or on the measuring surface? Then of course you wouldn't see the other particles underneath. When we fuse this into a fuse bead, then we have to see this as just as one homogeneous ideal sample, because then all these particles are dissolved into the glass, and it's like in a liquid, like you put salt in a water. It's completely dissolved. The original particles are disappeared and they are completely homogeneous, dissolved. Still, we have the same physical problem that we have to go into our sample with the exciting X-rays, and the fluorescence radiation has to go out, probably a little bit deeper than in the solid case, because the glass matrix from itself is a bit less absorbing the X-rays, but more or less it will be the same deepness. There is not such a big difference. So let us look a little bit more in detail. That means here I present you different materials, so like graphite. This could be also a liquid like water or oil or a polymer sample. And here I present you the elements in increasing atomic numbers orders. And so that means the light elements are in the beginning, the heavy elements are here down. And you see on the penetration that the very light elements, we are in the range of micrometers, in the middle range in millimeters, and further down in centimeters. So it makes a big difference what element you are watching and what is your matrix. Because if you go to a heavier matrix, like a rock sample, for example, and then you see that because the mean atomic number of the matrix is now higher, this sample will absorb X-rays more heavily. That means that your penetration is decreasing. So there is now more elements coming from the micrometer range than only the heavier ones in millimeter and the very heavy elements in the centimeter. And if you go to a metal matrix, you see that more or less all elements are coming from the surface of your sample. And this is, of course, something you have to have in mind. If you just pour a metal powder into a sample cup, you know that just the first micrometers are analyzed, and everything which is deeper in the sample will be never seen by the X-ray. Yeah? So the classical example, you have a bar made from gold, and you want to know if it's really real gold, then you just would touch the surface with your X-ray, and you can't really look inside. And here just focus on three elements: a very light element, a middle range like iron, and a heavy element. And here you see again clearly how the penetration depth changes and how this makes a difference. But of course, it's always good to have an example. So this would be a press pellet here, press pellet from a dolomite. It's a standard reference material. So we know that the particle size is something in the range of 50 to 150 micrometer. And I put here the elements from a very light one in the order to iron. And I put here the penetration depth for these elements. And then you can see that sodium is just analyzed in the surface of this press pellet, while potassium perhaps is already analyzed in one full particle, and iron is analyzed perhaps in 3 layers of particles. And this is then how it changes really the focus. So if we really have this press pellet and we just analyze the surface for the element we are looking, it makes a big difference when we have the same sample in a fuse speed. And of course, the penetration is still the same, but now the volume we analyze is much more representative than here in a press pellet. And this is the reason why, for example, if you have a calibration of silicon oxide in press pellets and the same calibration in fusion, that the error is improving like a factor of 5, just because the fact of that the sample preparation changed from press pellet to fuse speed. Okay, but then let me explain you in detail how the sample preparation works. So we will start with sample cups. So here you have normally 2 rings. In between you make a transparent film, and then you just assemble them to 1 cup. You should make sure that the film is really stretched very nicely so that you have no folds, because otherwise this will disturb your measurement. Then you pour your sample into the cup, and finally, yeah, it could look like this one here. So you have your powder sitting there. So all these 4 materials I showed you in the beginning, we have prepared like this, and then later on Carmen will show you the measurements for it. So what can you do wrong when you prepare sample cups? You should really make sure that the ring fits very nicely, that you have no folds here in your sample cup, that is really stretched, because the distance of this ring to the X-ray tube will define the intensity. And if the film is not properly on the right height, then of course you get a different intensity from your sample. So therefore it's so important that this is perfectly prepared, like in this case. But also the film makes a difference. There are different films in the market, mostly mylar and polypropylene. Mylar is a polyester. So polyester has oxygen, carbon and hydrogen, while polypropylene just has carbon and hydrogen. And so that means mylar films absorb X-rays much more. And this is why if we look here on this graph, we set the thinnest mylar film to 100%. And if you have another mylar film, which is thicker, you see you always reduce transparency down to 60%. If you go to a thicker one, to 35, and even a very thick one, you have only 10% of the intensity left for sodium here. It will be better then for higher atomic numbers, but it goes at least until chlorine. You still see the effect. When you go further in the periodic table, I think at calcium, then it's disappeared. Then it doesn't play a role what film you use finally, because then they're all the same in the transparency. But for the very light elements, it makes a big difference. And I would say typical films which are used is when we just do powder analysis, polypropylene 6 microns like this one, which also lasts to high power X-rays. If you use energy dispersive, you could also use the 4 micron polypropylene. But of course, there makes also a difference if you use polypropylene or mylar, because there are impurities, especially in the mylar film. It contains calcium and phosphorus. So if you want to analyze these as trace elements, you have to be aware of this. And that's why for powders, I would always choose the polypropylene films because they are clean. Only for liquid analysis, it might make a difference. But of course, today we just talk about powders. We prepared now these samples in the sample cups, and what Carmen will show later on is that for the sand, we made it just as a coarse material, and we also grinded it so that we have a fine. So you will see a difference in the particle size, just as the loose powder. Here again, you see already that this powder is much finer than the other one. And we will be curious how this will result in the XRF quantification. So press pellets, what is there the way to do? You have your sample, you mix it with a binder, then you press it, and then you get your pellet. But of course, it's not always as easy. You could also use other kind of tools like aluminum cups or rings, and this I will show you in the next slide. Here I have a complete step-by-step procedure how you can make press pellets. The first thing you should make sure is that your sample has a certain fineness, that your particle size is reduced, because we have seen that particle size makes a difference when you want to measure deeper in your sample. And so you would use a grinder. You weigh then about 4 grams of your grinded sample. Then you would add a binder, and then very important, you have to mix it so that you have a homogeneous mixture. Then, before you put it in your die, there are several options. For example, you could adhere a pellet film to avoid contamination from your pellet die, because this is always hardened steel, and that means you will find iron and chromium. And when you are looking for these elements as traces, like iron in a sand or chromium in a geological sample, then of course you will see that little impurity from the pressing. Then the film makes sense, or just to keep the plates cleaned during the preparation. You could use aluminum cups. It's nice to write on them, and then it will already stabilize your pellet from 2 sides. When you have decided for that, then you pour your powder in your die, you press it, and then of course you get a nice pellet. The quality point I check always is that when you take your finger over it, that there's no dust on your finger, and that when I go to the margins, that also they remain stable without breaking down. Here we will show you then coarse and fine particles, and you see then differently prepared. Here you can see always the press pellet with the coarse particles and the fine particles, and then of course from the others we just use the fine ones. And this is the press we used to make the press pellet. Okay, then last but not least, we look into the fusion preparation. So typically we will take something like 1 gram sample, an 8 gram flux, and if necessary, a non-wetting agent. We mix this all together, then we heat it up, then we agitate it when it's really liquid, and then we pour it into a preheated mold so that we get a homogeneous glass melt without any tensions. And then when we cool it down, there is no risk that it breaks. Yeah, so this is the fusion process has to make sure that all particles are really digested so that it's a complete solution, and then that it's really homogeneous before you pour, and then you have a homogeneous glass, and the glass is really considered as the ideal sample. But you have to think about to pre-treat your samples, because we have sometimes also volatile parts like carbonates or halogens or water. And to make sure that the fusion process is of a high quality, we in our case also prepared a few of the samples and calcined them, so that in the end we have 100% oxides. We use them for the fusion. Carmen will indicate on her analysis if it was pre-treated or not. And here, last but not least, this is how you see it. Here the different samples were prepared. The flux was weighed into the crucible, then the sample was added. We mix it a little bit so that in the fusion process you have a good contact between sample and flux. Then in this case it was on the gas machine fused, and then you get your nice glass bead. And yeah, these were the beads from all the four materials Carmen got then for the analysis. So last but not least, to summarize, we have prepared the powders as fused bead, and a lot of powders we have prepared in a sample cup, loose powder, press pellet, and fused bead. And now we are curious to see what Carmen made out of it.
Thank you very much for the interesting talk. Okay, so
I
I'm going
just
to.
stop mine.
Are you? Okay. Yes. Okay. So I should be able to share my screen, and hopefully you will see the.
I just see there's a question in the chat. So we will answer all questions in the end, but you can already write the questions to the questions part here.
I think you can see the correct screen, right? Right.
Yes, that's fine.
Very good. Okay, so I would love to show you the influence that the sample preparation has basically on the analytical results. Yeah. So this is our products that we have. We have sequential and simultaneous main QC instruments, if you like to call it that, and they are called the Primus series. And we also have the benchtop instrument, which is like a backup instrument, like a super mini, which doesn't need any ancillaries, but they are all wavelength dispersive instruments. So in my talk, I will do the measurements. I did all the measurements basically on what we call our Primus 4 instrument. Yeah, I just quickly talk a little bit about it. All the measurements were conducted with special analytical programs developed for each type of measurement. So fusion was with a fusion method, loose powder with a loose powder method, and of course pressed powder with a pressed powder method. So what's quite nice with the Primus instrument is that we have the possibility to get quite a lot of intensity from our measurements. So you will see some spectra. And the reason for this is because we have a really thin beryllium window on our X-ray tube, which is a 4 kilowatt tube. And in fusion and pressed powders, I used what we call automatic pressure control, which ensures that we have a lot of stability in terms of vacuum. So this is important for reproducible results. So we can basically measure our samples either with a semi-quantitative method, which is something like this. So we can build our spectra and look at the spectra and look at the elements that coexist with each other. So this is an example of a semi-quantitative method, or we can measure samples with a calibration method. So as I mentioned, if you want to measure loose powder, it should have a matching calibration for that, and pressed and fusion, for example. So let's look at the example of calcium carbonate, which is basically limestone. So as you saw, we got some a nice prepared samples. Here's the example of the pressed powder. Here's the example of some fusion, loose powder analysis in a cup. And the limestone was milled basically and dried. So of course, the dried material was dried at a certain temperature, and we also calcined this material to get what we call the carbonate portion of the limestone. So of course, in order to prepare the pressed powder, it's really important to have the correct particle size. So the finely milled sample was mixed with the wax and pressed. So you can see it here. Here we have the preparation for the fusion, which Rainer already explained, and the type of flux and the dilution for and the fusion parameters, yeah, and the fusion program, yeah. The loose powder was prepared in the cup and basically measured with the method. So here we can see an example of calcium, yeah, in the first spectra. So here we can see, for example, that the loose powder and the pressed powder have almost the same intensities, but of course with the fusion, it's much lower because the matrix is really different. And here we have an example of phosphorus, of sulfur, where we can see that the intensity of the sulfur K alpha is much higher with a pressed powder than it is with a loose powder. And the reason for this is because, of course, a pressed powder is a more compact specimen, and we get a better intensity for this, whereas a loose powder has, unfortunately, voids and spaces in between. So it's not always the best in terms of getting the best signal, but we get a decent signal. But this is why we have the difference, yeah? What about chlorine? Chlorine basically is a trace element in the limestone, and we don't get a signal for fusion because, of course, it's a trace element and it's a light element. And so we lose this very trace element with a fusion in this kind of matrix. But of course, here you can see that we get, once again, a much higher intensity for a pressed versus a loose powder. Additionally, phosphorus, another light element, which is also from the very top micron layer, again, we have a really nice signal and a much higher signal on a pressed powder than a loose powder. Going more into the light elements, because these are the critical ones, you can see again the signal for alumina on a pressed powder is much higher, magnesium as well, silica as well. And what about sodium? So sodium is a problem with a loose powder because basically the film that we use in the cup will absorb the fluorescent X-ray of sodium. So of course we see a very reduced signal, and therefore this is not a suitable method to measure sodium with a loose powder method. Yeah. Fusion, we also have a reduced signal because once again the sodium is a volatile element, and once again yes, we have a different matrix here, and of course the best method for sodium in this case would be a pressed powder. So we get a really nice, decent signal. So here we have an example of the heavy element spectra, and of course here you can see that in the green we have the characteristic, of course in green we have the fusion, and we have a much higher sort of Compton peak here, and this really shows the difference in the matrix, yeah? So we often use this Compton method to look at the matrix of the sample. So this really shows you the differences between a fusion, a loose powder, and a pressed powder. Here we have a signal of iodine because this comes from the non-weighting agent that's used during the preparation of the fused bead. And additionally, if we look at our heavy elements that are trace elements like strontium, we get really nice signal for our pressed and loose powder. So because strontium is a heavy element, we don't see the significant difference between pressed and fusion, between pressed and loose powder. Yes. Here we have another spectra where we take out the characteristic lines from the X-ray tube. So here we use a primary beam filter, and we can see some iron and nickel. So important to know is that trace elements are not possible with a fused bead. So that's clear. So of course, here's a table showing you the results and the differences between pressed powder, fusion, and loose powder in terms of concentrations, including the loss on ignition. Yes, we calculated the calcium carbonate purity by using the calcium oxide that we got. And in order to get these concentrations, it was very important to use dedicated quantitative methods. So basically, fusion is known as our reference method. And once again, it has the highest accuracy, since this method really ensures that we have a homogeneous sample, a defined density, but it is not suitable for traces and volatile elements, as you can see in blue. Loose powder is not suitable for the measurement of fluorine and sodium because the film will absorb the fluorescent X-ray. And here we can just see the differences between the concentrations that we have for the light elements and the heavier elements, going from pressed, fusion, and loose powder. So remember, the loose powder doesn't have that defined density. So sometimes we will have differences, especially on elements like magnesium or sodium. So here you can see, for example, on the sodium, we only pick it up on a pressed powder. Yeah. So this is a very important factor. So imagine if you measure a loose powder and you don't pick up the sodium here because of the film absorption. So you need to bear these things in mind when you do a preparation and an analysis, because this is the reasons. Yeah, chlorine is not picked up in the fusion because of the trace component, and of course, yes, it's volatile. Yes. Let's look at another kind of sample like sodium sulfate. So here we have once again the preparation of pressed, fusion, and loose powder. So you can have a look at it in detail when you get your download package. But always important to always dry your material. Very often, analytically, we forget that moisture can play a role, and I know it's very small, but we need to prove that we need to dry our sample correctly. So this is also a very important factor. So again, we can see some data for pressed powder, fusion, and loose powder. So in the sodium sulfate, we have trace amount of calcium, of course, but you can see a massive amount of intensity that we can get on a pressed powder. What about a trace element like potassium? So potassium is a light element, but it's much heavier than calcium. So the differences are not so significant here because of the analyzing depth and also its energy. Yeah. If we look at chlorine, there is definitely almost a similar intensity here on loose and pressed powder. Here we have the rhodium L line. But what about an element like sulfur? So sulfur, the signal is perfect on a pressed powder. So very nice intensity, nice background measurement can be done here. So when you develop your method, it's important to have a nice signal So peak to background ratio should be good. If we look at something like phosphorus, we can see the pressed powder has a much nicer signal in comparison to the others. And if we look at silica, which is a trace element here, again, the pressed powder gives a decent signal. Magnesium is a very complicated element because it's very light and we require a good stable vacuum level. So again, the peak to background ratio of a pressed powder is very nice here. And of course, on a pressed powder, we get a very small signal because it's a trace element. So alumina, we have a nice decent signal for the pressed powder. Yeah. What about the massive amount of sodium that's present here? So here we can see the influence of a defined density and the influence of pressing the powder. So yes, we get decent signals for the sodium in all three methods, but we can really see the influence of the pressure that we use for pressing the powder and the defined density. Of course, you ask yourself the question, why do we get a decent signal with a loose powder? We still get a signal because it's a massive amount of sodium here, but the film will absorb some of the fluorescent X-ray of sodium, but because it's a very high concentration, it's kind of negligible, yeah? But you can see a really nice explanation why loose powder and pressed powder have the differences, yes? Here we have the heavy element spectra, again showing the different matrices with the Compton line. Here we have the primary beam filter to look at the antimony, for example. We don't pick it up as a trace element on fusion, but we do pick it up with loose and pressed powder. Then we can see a table here showing the analytical results. And once again, we can see the differences in the results between loose powder, pressed powder, and fused bead. We calculated the purity based on the sodium content that we obtained from the different methods. And as you can see, in some cases, we do not pick up the trace elements in the fusion, so like the phosphorus and the potassium and the antimony, yes? So this is why normally in XRF we try to have a combination of pressed and fusion to give major, minor, and trace element analysis, yes? So what is talc? Talc is basically a hydrated magnesium silicate sample. Yeah, it's quite an interesting material because we would like to see the influence that we have on pressed, fusion, and loose powder. So here, once again, we have the details about the moisture of the material, and of course, the calcination. So it's important to calcine the material because it's a hydrated magnesium silicate. Yeah. So of course, you can see that the loss on ignition is quite high here because of the hydrated part of this material. So this is later used to complement the analysis for pressed, fusion, and loose powder. Yes. So here we can see the light element spectra for the talc. And basically you can see the great signals that we can get for calcium for loose powder and pressed powder. Yeah, almost the same. Yeah, and then of course the fusion is a little bit more reduced because of the matrix of the sample. Here, potassium is a trace element, so once again, the pressed powder will give a much better signal for you when you do your method development, yeah? And the same with the sulfur. The phosphorus, using here the curved crystal, which is the germanium curved crystal, we can see there are slight differences between pressed powder and loose powder in terms of the intensities. Yeah. If we look at silica, which is a major composition of the clay, we can see that, of course, the pressed powder gives you a very nice signal in comparison to the loose powder, for example. Yeah, magnesium as well, very nice pressed powder signal. Yeah, sodium is a very small trace element here, but we can see that on the pressed powder we have a certain degree of sodium intensity here for the sodium. It's not picked up on the loose powder because of the film that will absorb this. Alumina is also a major composition of the clay material, and again we can see a really nice, more intense line for the pressed powder. Yeah. Here we have the heavy element spectra, and we can see again that this material contains different kinds of heavy elements like bromine and strontium. We have the overlap with zirconium, yeah, and the conformation of the corresponding K alpha, K beta lines. Yes, here we looked at the iron and the manganese, which is on the shoulder of the iron. And of course, you can see that there will be slight differences on the background measurement, but on fusion, pressed powder, and loose powder, we get exactly the same signal because it's a heavy element. Yeah. Here we have a table showing the comparison of loose powder, pressed powder fusion of the hydrated magnesium silicate. And again, you can see that we have the differences with the magnesium here. And of course, quite similar results on the silicates. But of course, the fusion was not able to pick up ppm levels of the sodium or even, for example, the zirconium at that particular level. Yes. So the analysis is complemented here with the loss on ignition. Yeah. So here you can see a nice diagram showing you the differences of magnesium and silica and calcium. So of course, why do we have these differences on the magnesium values for the hydrated magnesium clay, yeah, silicate clay? So of course, the pressed powder has a certain matrix, and we have a certain error related here to particle size and the pressing. Here we have a very homogeneous sample with a defined density, and also we have a defined density here. And of course, the loose powder has the disadvantage that we have some problems with, of course, the density of the material. It's not compact. There are voids and spaces in between. But of course, remember what Rainer said, magnesium is a light element, and it's measured from the very top micron layer. So this is why we have these differences. So all these small influences will influence the result, yeah? Okay, so here's a nice example to show you the differences between a coarse particle and a fine particle. So here we used sand, which is a nice example. So the coarse particles for the sand were more than 90 micron, and for the fine particles we had less than 45 micron. So just a reminder, of course, if you look at a pressed powder, we have to read these kind of elements from like a 20 micron layer. These group of elements are read between 50 to 100 micron, and the heavier elements are much deeper within the sample. So yeah, try to consider this. So of course, the focus here is on intensity. So if you have large grain sizes, we have lower intensities. If you have smaller grain sizes, we have higher intensities. If you have more pressure to form a pressed powder, we also have higher intensities. So the intensities that we get depend on particle size and pressure as well. So if we look at the particle size effect, you can see here, the finer the particle size, the maximum intensity we get, the higher the particle size, or the bigger the particle size, of course, the lower the intensity. So this is a very important diagram for you to remember. What about the analytical impact on a mineralogical effect? So the different kinds of mineral forms in a pressed powder. So if you look at calcium, calcium could be as calcium carbonate, calcium hydroxide, calcium fluoride. So the problem is we have different matrices here. So of course, with the pressed powder, we have to have different calibrations for the different materials. But with fusion, of course, we solve this issue. Yeah. Okay, so let's look at these differences in the sand. So if you look here at silica, we can definitely see the huge impact and the huge influence on the fineness of the material and the influence of the pressure. So the very fine sand that we pressed gives you much more intensity than a sand that has been coarsely pressed. Yeah, so you can really see that on the silica, and you see that also on the zirconium even, because of course, remember what we said. We said if you have coarse particles, we could mask the detection of the zirconium even. Yeah, you know, so it really depends on how we press the material in terms of intensities and so on. Yes. So calcium, we also see a dramatic influence here on the granulate fineness and the influence of pressure, and the same with potassium. If we look at sulfur, it's a trace element here, but you can also see that the finer particles which are pressed gives you a much more intensity than a coarse sand that's pressed. So of course, if you don't have a correctly pressed powder with the correct particle size, you may not even pick up elements like sodium or phosphorus, for example. Yeah. What about magnesium? So of course, magnesium, we can see that we can get a decent signal if we have a very finely reduced particle and pressed with a defined density. Alumina, we can also see a dramatic influence on the fineness and the pressure in terms of intensities. Yeah. Okay, well, let's look at the sand now in terms of pressed and loose powder. So here we can see that we don't even really get a decent signal for a coarse pressed powder or even a loose powder. Yeah, but what about silica? We can see that the pressed powder has a much better intensity, and the same with alumina. Yes, same with calcium. And zirconium, and the heavier elements like titanium and iron are much better on the pressed powder. Magnesium, we can see that we get also a decent signal with the pressed powder, so finer particles, higher pressure provides much higher intensities. And even it's imperative that we stick to the same particle size all the time. Okay, so in conclusion, the light element spectra for pressed, loose, and fusion are shown here for calcium and potassium, sulfur and phosphorus. So always we have a much higher intensity for the pressed powder. The same with the silica and alumina. And again, we look at the heavy element spectra. Yes. This is the last table to show you the differences in the results for the sand, for pressed powder, loose powder, fused beads. So again, not such a dramatic effect on the silica values that we obtain, but of course we do not pick up trace elements with, for example, the loose powder method here, or even phosphorus as a trace element in fusion. Yeah. Okay, so the last thing that I wanted to just say is that we need to consider the best analytical solution. So would you choose pressed or fusion? So of course, it depends really on the skill level that you have in the lab, how many samples you need to measure, what kind of errors you will get with pressed powder, what kind of results you will get with fusion. Of course, it offers much higher accuracy, but you need a higher skill level. You need to have a bit more reagents in this place, so it means it's more time consuming and costly, but it is probably the reference method for your lab. So the optimal sample preparation method should be chosen considering the precision and the cost and the preparation time. So just very briefly, remember this diagram that I showed you on the analytical impacts of pressed powder and fusion. So of course, pressed powder has this drawback with the matrix of the calcium in this case, but fusion solves this issue. Yeah, so it means that we get a more homogeneous sample. We take away the matrix and the mineralogy, and therefore we can have one calibration for these different minerals forms. Yeah. So yes, please try to consider the influences in terms of the analytical surface. So as Rainer said, this is a very homogeneous sample, but the drawback is, of course, fusion cannot do traces and the volatile elements. But then, of course, if you choose the press powder method, ensure that particle size is correct, pressing is correct. Yeah. But what about loose powder? So you can see that we can also do loose powder analysis, but it is quite complicated because, of course, we also need to make sure that the sample is dried properly. It has been reduced, the particle size has been reduced properly. But the drawback with the loose powder method is, of course, that it could be used mainly for a qualitative analysis, maybe not, for example, a production control method, or even anything to do with very high precision and accuracy, because there may be differences. Maybe some of the people will not put the right amount of powder in here, even though you have a work instruction to say how much to put into the cup. So therefore we can summarize and say that loose powder has a medium accuracy, and it's more like a semi-quantitative analysis, and a pressed powder method also has a medium accuracy, but it can be used for quality control. And then fusion has the highest degree of accuracy, but is known as our reference method. Yes, so maybe Rainer, you would like to do a summary for us?
Yes, I'm here. Yeah. So, yeah, I think I hope you could impressively see. I mean, you have to click the buttons, I think.
Certainly.
Right. So I think we could easily see that the sample preparation makes a big influence to the result, and that means as more work you invest, as more you get precision and trueness out of it. That is for sure. And in all these questions I answered already, I already answered 26 questions while you were talking here. All these questions are the same. So how can we make a reproducible sample preparation? And what is the effect really of grinding down, of pressing, of fusion to the element of interest in the end? And it's always the same. The light elements, they ask us to do a lot of efforts to get a good precision and trueness. The heavier elements are not so critical. There you could also go to less work like loose powder and press pellet. And I think Carmen presented impressively how this then is presented in the final results. Okay, so I thank everybody, also Carmen, for all these
Thanks, Rainer.
presentation and for the questions already, but now we still have a few questions left for you, Carmen, and of course you can put more into it. Perhaps, Carmen, do you see the F&A
Oh yes,
part?
let
So there is the first question is something about Primus and Supermini.
I'm just oh you in the
F&A, F&A.
in the chat? No.
No, it's in the F&A part. There's another button, F and A.
Unfortunately, I don't see it, but you can ask me. Don't worry.
Okay, so hello, quick question. Since both the Primus 4 and the Super Mini operate under vacuum conditions during analysis, is there any concern that pressed pellet samples could release particles that might detach from the pellet and potentially damage the detector?
Ah, okay. So yes, that's a nice question. So yes, we have a Primus instrument and a Super Mini, and they both use a vacuum, yes, for the measurements of press powder and also fused beads. So we need to make sure from the preparation side that our pressed powder is pressed properly, yes? Because if it's not pressed properly, yes, you can have some dust falling from the pressed powder. But what's the beauty of a Primus 4? Well, we have a geometry, X-ray tube is above, and if the particles fall, it falls into a cup. But if you have a Super Mini, well, it's the other way. So the cup is like this and the X-ray tube is below. So yes, unfortunately, if there are loose particles, it can fall on top of your X-ray tube. So that's why it's very important that we prepare the sample correctly. But it will not go into your detector, like the question said. No. So it will just fall on top of the X-ray tube. Yes?
Okay, thank you, Carmen. There was a question probably related to one of the transparencies. All these pellets are analyzed in the same calibration, constructed using a few speed standards. Probably not. I mean, all your calibrations were done with the same sample preparation.
Exactly, the same sample preparation. So it's very important when you measure a sample that the sample matches what the preparation of the calibration method is. So if it's a press powder, you need to measure it on a press powder method. If you measure a fusion, it must be on a fusion method. And if it's a loose powder, you need to measure it on a loose powder method. Yeah, so it's very important to have the same preparation and the same preparation for the standards and the samples. Yeah.
Okay, thank you. Then there was, okay, which software you recommend for this? We don't know which. Perhaps you can write again in the chat to ask what transparency or what analysis your question is to. Then
Yeah,
I'm
yeah.
going down. There is Choma. He is writing about using ethanol as grinding aid. And I answered the question already before. I think this is a very clever way to do grinding, that you add some alcohol, and the alcohol is, of course, cleaning the mill. It sticks all the particles together, but then it's disappearing. So it's on one side it helps to grind your sample down, but at the end it's disappeared and you have a clean mill and a fine powder. It's, in my opinion, a very nice way to do that.
Yeah, I used to use it many years in my laboratory. It works extremely well.
Yeah,
Yes.
yeah. We are getting requests for analysis of very small amount of powder, 50 to 100 milligram. Particle size is mixed and they don't want to grind it up as they want to use it in other experiments. Any ideas in approach?
Yes, exactly. So at Rigaku, we have very special sample holders that can accommodate these very strange, tiny little samples that you don't want to destroy. So yes, we have like a sample board, and you can pack the loose powder into the board with a film and a snap-on ring. But remember, it's very semi-quantitative. So you would use, in this case, a semi-quantitative analysis, yeah? So it won't be a very high precision or high accurate method, yeah, based on the calibration, yeah. So I can contact you and we can give you the solution, yeah.
Okay, thank you, Carmen. Then there's another question, which is the better method for furnace slacks. So, of course, I know that slack analysis in routine is done by press pellet, but you always need to have a reference value because the slacks are very individual. So, what we do normally is that we have a fusion method to get the values, the concentrations from the samples. And with these concentration, then you set up your press pellet calibration to do then the routine job. I think that's the best way to go there.
Yes, yes, definitely.
Another question is, if my pellet press produces pellet with 32 millimeter diameter and my XRF holding diameter is exactly 32, then how to adjust it? So I understand that your press pellet is a little bit bigger or doesn't fit in your holder.
So in this case, if you have a 32 millimeter press powder, you can get different mask, sample cup masks. So at Rigaku, yeah. So you can, for example, take a 27 millimeter. So that means you will only measure 27 millimeter from your 32 millimeter. Because if you put it in a 30 millimeter, it might not fit exactly, yeah. But actually, I have 32 millimeter press powders in my lab, and I use a 30 millimeter mask. So this is the very big advantage of a Primus 4 holder, because we have tube above, we push the sample up, and so because we push the sample up, we can position the sample that we get maximum analytical surface for our readings, yeah? But those are the two options, yeah?
I also would, if it really falls through the hole, then I would do it in a sample cup as
Yeah.
a first trial. This is sometimes that we have samples which are too small for our holders. Then a sample cup will make a solution, but of course you have a film. Yeah, additionally, this
Yeah,
has to be taken into account.
exactly.
There's another question. Is there any application note on cerium oxide measurement in solar panels?
Yes, we have that on our website actually. So if you go to www.rigaku.com, you will find some examples there. Or I could also be in touch with you if you really want to know the application. Yeah.
Okay, there's another question. What preparation method do you recommend for soils with organic material to be analyzed in the S8 Tiger? So I would say organic material in soil, or let me say it a different way. When you analyze soils, normally you go two ways. You make a press pellet to get all the trace elements, and you make a few speed to get all the major elements in high precision. And then you combine both to get the full geological analysis. What else do we have? Can you please advise a method on using cereox? Should it be mixed with milled sample manually or by a special mixing machine? You could mix it manually, but it takes a while and you have really to do it in a way that it's completely mixed. We use the small muck mixer, which is a very simple machine, which after 1 minute or so has a completely homogeneous mixture. I think that's a very small investment for a very good output. So I would always recommend to do it in that way.
Yeah.
What do we have here? I was using a Super Mini 200 for the analysis. Is that software having the palette thickness correction for thinner specimens? It goes further. I read it first. I did analysis of pellet of calcium silicate hydrate using two different modes, metal alloy and oxide powder. For the same pellet, the calcium silicon ratio is under predicting in oxide powder mode. Is it a correct way to analyze the oxide compounds in metal alloy mode?
Okay, so yes, in the Super Mini 200, in our semi-quantitative section of the software, you can, for example, choose the different matrices of sample that you have. So it's really important that you choose the correct matrix, yeah? So don't try to measure a press powder with a metal template, for example, or yeah, a polymer template, yeah? So it's important to just help the software a little bit about the matrix. We can always, after the measurement, actually recalculate and reprocess the result. But yes, the fundamental parameters needs to know a little bit about the matrix of the sample to make the correct estimation for a semi-quantitative analysis. Okay, so try to remember this. And of course, if you want to convert from oxide to element, then you can change in the calculation mode between oxide and element, yeah? It's very easy in the software. So if you want to report strontium as strontium instead of strontium oxide, it's possible to just, for example, change it in the software and reprocess the result, yeah?
So there's another question. Hi, Carmen. What flux would you recommend for fly ash composition?
Oh, okay. Hi, Lindy. I think it is. Right. I see it now.
Oh, okay, good, good. Okay.
Yes. Yeah, basically, the fly ash, we could use our 100% lithium tetraborate mixed without any mixture. I think this is quite suitable for this kind of material.
Yeah.
Yeah.
Yeah, I would agree as well, yes. Then there's another question. What preparation method can be used for filings from the steel industry? Filings are, I think, small metal particles from steel, and you could just analyze it like it is in a sample cup, and use your standardless software to get an idea about what steel it is. And also you could make a few speed of it. That is what we do when we have 3D metal powders and we want to quantify them. Then we make oxidation first, and then we make a few speed first, and then you have a complete analysis of all your major elements in the steel. So this depends a little bit on what is your idea. If you just want to identify the alloy, or you need more precise analysis. So what else? Please. There's someone who would like to have a webinar for matrix correction for calibration. Yeah. Okay, good idea.
Good idea. We
We,
can do
we keep it in mind.
it.
What kind of possibilities do I have if I can get a homogeneous fusion solution? By preparing a fused speed with sludge ash, it always cracks by cooling down at about 100 degrees. The solution has a little trace swimming on the surface in the crucible. Okay, when a bead cracks in the end, it means that you have tension in your glass. And tension could have different reasons. One reason is that you have one particle which was not dissolved. Or it could be that your bead stucks to the metal mold, and when the mold is shrinking because of cooling, it just cracks your bead. So what you should do is that either you increase your temperature a bit and your time so that your material dissolves really 100% into the flux. And the other thing you could do is to avoid the sticking, that you add some non-wetting agents. And when this, what you said, there's swimming something on top, this could be perhaps also some carbon. I know this from continuous casting powders. Then we have carbon swimming on top. That means we just let it longer fuse so that everything burns away and converts into oxides so that this problem is going away. So that is what I would recommend here. Then there's another question, is grinding the sample directly with the binder a good solution? Probably not, because it sticks to the wall and it makes a lot of mess. So either you use this alcohol idea so that you grind down and then add the binder later, or you go to a cellulose, which is a kind of compromise between grinding and binding. So I don't know, Carmen, you can add something.
Yeah, so of course I worked in the cement industry for many years, and we had a lot of samples that we had to prepare. So it's very important to first remember that you should try to reduce your particle size to less than 45 micron if you are looking for pressed powder. And then once you've ground the sample correctly, then it's a good idea to then add the binder, but you can mix it in a mixer mill. So like from you get different kinds from different suppliers, but it's like a little jar. I think Rainer had it on his slides, and you can use this kind of jar to mix the binder and the reduced samples, yeah. Or you can even have the little vials, the plastic vials with the mixing balls that you can get from FLUXANA as well for making the pressed powder. But I know if you have a very high sample volume, it's maybe just a good idea to use your equipment to very quickly mix the two. So it's very important that you first reduce particle size. Yeah.
So there's another question. Will you share the recording? Yes, everybody who is registered gets the link to the recording and the PDF for the presentation. Then there's another question. What is the ratio of solid sample to boric acid for making pellets? So I would say the boric acid was always used as a backing. So you
Yes.
don't mix it with your sample. And
Yes.
nowadays, because boric acid is considered as hazardous, we offer something like Boreox, which is a cellulose-based powder you could easily use to replace it. So you make first your powder in there, and you add then your sample on top, so that your sample is just sitting on top of your backing. What else do we have? Looking for rare earth in concrete. Not found any CRMs. That's true. There is really nothing in the market. Is there any guide for making your own calibration standards? What I would recommend here is that either you go to Fusion, then you can use pure chemicals to set up your standards, or
Yes.
you let it analyze, for example, in our lab. So we give you the concentration values, and you can set up then your press pellet calibration based on these values. That would be a solution, I think. So the questions are getting low now.
I think
Yes.
that was the one lady that asked the question previously. The binder is cellulose based, so she was asking about the grinding of the sample and the binder. Yeah.
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 Exactly. Yeah. Yeah. There is, I think that is all. I think any question which is still open can be placed directly to us. So you can just send it in, and then we can clarify it in detail. So I think we thank everybody. We had 26 questions answered, and even 25 more now after it. So more than 50 questions. So this is a very, very good response. I thank you all very much for attending this joint webinar. And yeah, also Carmen, thank you very much for your efforts.
Yes, thank you as well, Rainer, and thank
And
you to the audience as well. We really
yeah,
enjoyed it and look forward to the future webinars.
okay. It was a pleasure. Thank you, everybody, and bye bye.
Thank you. Bye.